Our next speaker is coming from Zoomland, specifically JPL. Patrick Bjornstad is a systems engineer and data scientist at JPL, and will be presenting his slides. Patrick, are you ready?
So thank you guys for attending today. As Jay said, I am coming here remotely from JPL. I'm a systems engineer, but more of a data scientist, really, primarily working in the formulation world, the project formulation world. And today we're going to be talking about language models for structured data extraction from long-form documents. So just a quick overview before we get started, a little bit of what to expect. First, I'm going to try and kind of make a case for why we might need a tool for structured data extraction from long-form text. Next, I'm going to kind of introduce you guys to a case study project that allowed myself and my colleagues to kind of first start exploring LLMs and their capabilities. I'll talk about lessons learned and the things we leveraged on the LLM side and how they might relate to this idea of structured data extraction. And then finally, I'm going to talk about knowledge graphs specifically as a promising data structure. So how do we need structured data extraction? I think at the core, aerospace projects and defense projects, and more generally just engineering projects overall, multidisciplinary, and as such, they're kind of reliant on this buildup of domain knowledge and subject matter expertise over time. Historically speaking, this domain knowledge has been passed down and captured within organizations, primarily in long-form documents. These are both proprietary and public documents that can range from tens to hundreds to thousands of pages long. And while there's kind of this rich legacy of information captured there, they're more or less kind of been unwieldy to access, not only from a human perspective in the sense that it's hard for us to read thousands of pages quickly and truly understand what's going on, but also from kind of an integration with engineering tools and statistical models side of things, in the sense that historically there haven't been ways or methods to kind of directly inject the information captured in those documents with our tools. So if we come up with some way to kind of convert this textual information captured in these kind of niche technical documents into a more accessible, structured or semi-structured format, I think we stand to gain a lot from that. So like I said, a quick introduction of the project that introduced myself and some of my colleagues to LLMs and their text processing capabilities. A couple of months ago, we were given this text classification task, where we were given thousands of active NASA work contracts written to commercial vendors. And these are primarily characterized by this free-form text field that describes the type of work that the contract was soliciting. And the goal here was to categorize those contracts according to JPL's organizational structure. Specifically, what we wanted to do was assign each contract the most relevant JPL work division with the intent of answering the question of how is the increasing commercialization of the aerospace industry going to impact JPL, and where specifically at JPL is it going to impact the most? And so right around the same time that we started this project, we actually got access to a JPL pilot program wherein they gave people around lab access to an internally deployed and kind of walled off cloud instance of the GPT-4 API. And the key here is that it is safe for proprietary data. So a big reason why we chose GPT as opposed to maybe traditional NLP methods plus kind of a supervised learning classification approach was the fact that we didn't really have labeled data. And because these contract descriptions were very long, it was expensive for us to have a dedicated effort to go in and label a big data set to justify, good performance of the supervised learning model. So instead, by kind of leaning on the pre-training of GPT and these large language models, the fact that they've been trained on the entirety of the internet or most of it, and have kind of this ability to capture the semantics of language, it kind of minimizes our need for a ton of labeled data. And instead, we can kind of work from this kind of few-shot scheme that you guys may have heard about in the LLM world. And the idea here is that instead of having a large training set that you train on, instead you have a few very high-quality ground truth examples, which we collected from having subject matter experts label these contracts. Now, the main thing the main capability within GPT that enables us to actually perform classification rigorously is this idea of function calling. And this basically allows us to define a JSON schema for how the LLM should respond to a given prompt. And what this does for us in the classification world is allows us to force the model to choose from one of our predefined categories, instead of maybe potentially hallucinating one that didn't exist in the first place. Now, of course, to improve performance, we wanted to give the model as much context as possible. So the first thing we did as JPL engineers was try to provide it with as much information about JPL's work divisions and the type of work that they do, to try and give it a better understanding of what types of contracts will fall in each bucket. So we would write a description of each possible class to choose from, which basically describes the type of work that that JPL division is involved with. From there, we wanted a way to incorporate our ground truth information as well. And so we kind of created this idea of a refinement scheme, or a refinement, iterative refinement process of these class descriptions. So what we would do is feed in these human-written class descriptions to a language model, and then one by one, feed in these kind of few-shot ground truth labeled contracts that have been labeled by a subject matter expert. And we would say, you know, using the information you can learn from this example, update those descriptions. And so in this way, you can kind of iterate or repeat over your small kind of few-shot, quote-unquote, training set, and create a set of updated or trained descriptions from there. Using those, you can then kind of feed them into a classifier LLM alongside a new unlabeled query contract, and use the function calling feature I described to assign it to the most relevant class. Now, I'm not going to spend too much time on this slide specifically, but one alternative we did look at was the use of text embeddings alongside traditional classification models. For those of you who aren't familiar, the idea of a text embedding is instead of feeding in some input text to a language model and having it generate new text as a response, instead it encodes that input text and tries to map the semantics or the meaning of that input text to a high-dimensional feature vector that kind of encodes that meaning into that vector. And in this way, you can kind of use this text embedding as you would any other traditional feature within a kind of a traditional classification model, like an SVM or logistic regression or something like that. And so the reason we tried this is it was, you know, cheaper in terms of API costs per token than the text generation function calling approach. But the main problem we had here, obviously, is that it requires much more training data, because now we're working with kind of a strict supervised classification model. So for that reason, we focused mostly on the function calling approach that I outlined in the last slide. So in terms of results, I'm not going to linger kind of on the specific results too much. Obviously, a lot of that information is kind of proprietary to JPL. But the main lessons learned here is that we were really impressed with kind of how well GPT did, quote unquote, out of the box on such a kind of a niche task with these, you know, technical documents that aren't necessarily representative of kind of, you know, maybe the entire internet. We kind of just had to provide some general context about JPL and its structure, and it ended up doing a fairly impressive job. I think the thing we were most impressed with or interested in was this idea of function calling. Obviously, for the classification I described, we're only kind of tagging each contract with a single tag, but there's no reason that this function calling feature can't be used for more complex data structures. And so that brings us to the idea of kind of this general purpose text extraction. Now, one thing you might be asking yourself is, if we have something like text embeddings, as I described, that we can feed into statistical models, why would we need to be able to like transform the content of these documents into a more accessible format if the text embeddings kind of already allow us to encode the semantics of text and incorporate that into statistical models? And I think the key here is that, especially for very long chunks of text, there's a disadvantage with text embeddings that they tend to represent kind of the average of the input. And for long input sequences, this disadvantage kind of gets exacerbated. Beyond that, we can't necessarily, as humans, look at text embeddings and kind of understand and interpret the types of information that they're encoding. So we want something that is kind of simultaneously interpretable and usable both for humans and for machines as well. And that's where this kind of idea of function calling in the more complex data structures comes into play. So in this simple example I have in the diagram here at the bottom, you can imagine maybe a document or a piece of text describing a number of different instances that we're interested in. You could imagine defining some sort of JSON schema that encodes some sort of tabular format for features regarding those instances and having the language model read some chunk of text and return JSON objects representing instances of a table. So that's a simple example of kind of extracting structured data from a document using this function calling approach. Now, of course, with kind of the types of niche domain-specific documents that we're looking at, not everything is going to be kind of amenable to this tabular format. And I think that's where this idea of knowledge graphs comes into play. For those of you guys who are not familiar, knowledge graphs are kind of this graphical data structure whereby nodes or entities are connected using relationships or edges. And the characterizing feature of a knowledge graph versus other types of graphs is that both these nodes and edges are given kind of semantic textual representations. So in this way, I guess I should say the core unit of kind of a knowledge graph structure is this idea of a semantic triple, whereby two textual entities are connected using a textual relationship. And so this example I give here, Mars is destination of MSL, MSL being a JPL mission to Mars. You can see that the two entities, Mars and MSL, have been connected by this textual relationship that is primarily characterized by English language and the semantics of English language. Now, knowledge graphs have existed for a long time, and what they're kind of trying to do is represent the factual structure of the world. But I think historically they've been limited by the fact that to get the most out of them possible, it kind of relies on understanding the semantics of language so that we kind of understand what these entities and relationships represent. And this is where kind of the interplay and the synergy with language models comes into play. Namely, language models are adept at kind of capturing the semantics of language, but as we know, they kind of struggle with the factual structure of the world oftentimes, whereas knowledge graphs are kind of the exact complement of that. So you can imagine a lot of potential interplay and synergies between these two technologies. For those of you guys who are interested in that more generally, I'll point you to that paper that is linked in the top right of this slide. It kind of serves as an index of current and past research into the interplay between language models and knowledge graphs, including kind of covering some about using language models to generate knowledge graph structure. And that's what we're going to kind of focus on here today. I think there's two main use cases in terms of LLMs generating a knowledge graph. The first being the generation of knowledge graph vocabulary. So this is the idea of taking in some chunk of text and generating a set of choices for entities or relationships of what the knowledge graph could choose from, or what the nodes and relationships could be. And then the other side of the story would be generating the graph structure itself. And so you can imagine here defining with kind of the function calling feature I've been describing a JSON schema for a semantic triple where we have kind of two textual entities connected by a textual relationship. Now, why might having such a knowledge graph be useful to us? I think the key main point here is that knowledge graphs strike this great balance between being useful to humans in the sense that with something like a graph database, we can kind of query and explore and traverse a knowledge graph ourselves. And because we as humans understand the semantics of language, we're able to kind of understand the information that's captured there. But at the same time, there's also rich potential for integration with engineering tools and statistical models. The first thing I'll note is potential integration with modeling languages and ontologies. Those of you guys who are familiar with model-based systems engineering may see where I'm going here. But ultimately, underneath an ontology or modeling languages is a data structure that is very similar to a knowledge graph. So you could imagine kind of this rich integration, especially because modern modeling languages have things like built-in reasoning engines, things like consistency checkers, and in a lot of ways, they might be able to make up for a lot of the potential weaknesses of LLM-generated knowledge graphs. And then kind of on the more statistics, deep learning side of things, provided you have at least enough graph data, you could imagine doing something like a deep graph embedding, where this is kind of the same idea as a text embedding, but instead of just looking at kind of the semantics of text, we're also taking into account kind of the graphical structure as well. So the idea here is kind of creating an even richer vector representation for our entities and relationships, or maybe even entire graphs that we can then feed into statistical models and tools. A couple more slides here. Let me check the time. Okay, looks like we're doing okay. I'll try to wrap up quickly so we have time for questions. Obviously, I didn't want to give this presentation without having any idea of whether such a scheme is practical or would work. So this is just a very quick demo of using, vanilla GPT alongside a public Wikipedia passage. Here I'm looking at a Wikipedia passage about the Juno spacecraft's science goals and science instruments. And I basically just asked it to generate those semantic triples, kind of relating those instruments to the goals. And that's the result there I got on the right. It might be hard to see the details, but basically what it went and did is connected the instrument entities to the science goal entities using this relationship is used for. And I want to note that this is not using kind of any prompt engineering. This is not using any of the function calling to minimize hallucination that I kind of described earlier. This is just like super vanilla, like test to see if it works. So I think with kind of dedicated engineering effort that there's a lot of space for good results here. Now, of course, it wouldn't be a talk about generative AI or LLMs at this conference if we didn't talk about the need for, human-in-the-loop validation. The great news here is that with something like ontology or modeling language integration, there is some space for automated validation of generated graphs with those kind of reasoning engines or consistency checkers that I mentioned. But ultimately, to make sure that these triples are useful to us, there's probably going to have to be some sort of subject matter expert in the loop verifying the generated triples or vocabulary before feeding that into a graph database, or optionally, feeding it back into the LLM as an example to improve future performance. But I think obviously this workflow stands to be much more efficient than the manual alternative of having humans read these potentially thousands of pages and generating the knowledge graphs yourself. And when you take into account things like labor costs as well, it stands to be cheaper too. Just a quick summary, I think we're at a point in time where we can think of data, generally speaking, as information and not just numbers. Specifically, LLMs have kind of unlocked these huge volumes of textual data, this rich legacy of kind of domain-specific textual information that certain organizations have accumulated over time, but have historically been under-leveraged, I guess you could say. Personally, I think the knowledge graph data structure I described is kind of the perfect tool for the job, in the sense that it strikes this balance between flexibility of encoding kind of whatever type of information you want, but also being accessible to both humans and our tools and models. So I think with kind of this structured knowledge base, the amount of, the applications, the range of applications that, could build off of that is quite large and probably goes way beyond just the ones I mentioned here. I just want to put in a quick plug for the open source side of the language model world. Obviously, I talked about GPT mostly today, but I think that the open source side of things is definitely the future of this research, in the sense that it has a chance to be more efficient and data secure by kind of removing the need for cloud environments, but also the customizability aspect. You could imagine fine-tuning on documents before creating a knowledge graph, or similarly fine-tuning on the knowledge graph itself as a way to kind of domain specialize a language model, or kind of get it to build from first principle facts, as opposed to kind of hallucinating all over the place. So I think this is an interesting avenue of research. Hopefully you guys think the same. I'm sure I'm running up on time here now, so I will wrap it up. And if you guys have questions, I would love to hear them.
We have a few questions. Can you hear us, Patrick, through this?
Yeah.
Okay, perfect. So raise your hands again. Who was it first? We'll go to you first.
Good afternoon or good morning. Elizabeth Petty-Cornell from Stanford. Do you include uncertainties and probability in your knowledge graphs, or is it similar to Bayesian network, or do you assume that they are all deterministic, as in the kinds of models that we have for engineering systems that are deterministic?
Yeah. So in the described of using function calling, it would more or less determine. There's not going to be a probability associated with a given triple. I have seen some research referenced, I think, in that paper I linked in the one slide about kind of the synergies between LLMs and knowledge graphs, where they do kind of approach the problem as more of a traditional statistical or probabilistic problem, in which instead of kind of generating these triples directly, you generate a candidate triple and then try to assess the probability of that triple being kind of real or useful. So hopefully that kind of answers your question.
All right, I think we've got time for one more question.
Excellent presentation. Thank you. So ever since LLMs hit the scene, people have been talking about merging them with knowledge graphs, at least as far as I can tell. And there's been a lot of like, oh, this is a good way to mitigate hallucination. So I assume there's a lot of literature out there already about this. So I'm curious, like, what you saw in the literature, if you did, a lit review, and then how is yours different? Because I assume people have tried things to marry them, and I assume they have failed because it's not the status quo.
Yeah, so I would say the most of my research focused not on kind of the use of knowledge graphs to kind of ground language models and minimize hallucinations. I mentioned that obviously as a potential application there at the end. But I would say that even if these knowledge graphs aren't necessarily the be-all and end-all for kind of grounding these language models, there's still a lot of potential use cases for the information captured there in terms of like not even interfacing with the language model afterwards. I think with kind of a structured knowledge graph, as I mentioned, there's integration with things like modeling languages and model-based systems engineering, ultimately something like digital twin. So I think even if it doesn't prove super fruitful to integrate the knowledge graph directly with a language model after it's been created, I still think we stand to benefit a lot from the creation of them in the first place.
All right, let's thank our speaker.
Thank you, guys.